In this video, we're going to look at integration of circular functions. Now, it's not all the circular functions. The VCAR formula only lists the integral of sine of ax dx and the integral of cos ax dx. So we don't actually have any integral for tan in our Year 12 Methods course. We'll leave that for when you get to uni and do some advanced maths. But these are the formulas. The formula sheet doesn't have plus c on it. I've put it on there to remind you that for an indefinite integral, you should have a plus c. What I want to have a look at is the relationship between the derivative of sine ax, which is a cos x, and the reverse process where you actually find the integral of cos of ax. So a is just a constant. So if you integrate this right-hand side, you can bring the a out as a constant at the front and then divide both sides by a, which is where you get your integral formula from here. And the same with cos of ax. You find the derivative of cos ax, you get minus a sine x. So if you integrate this whole side, you can bring the minus a out as a common factor at the front and then divide through by minus a on both sides. What that actually means, and what one of the common things that students get mixed up with, is that when you compare, let's look at this here, when you compare the derivative and the integral of your trig functions for sine and cos, the sign of the derivative is opposite. So the sign of the derivative of cos is the opposite sign. So derivative of cos is negative, so the integral of cos is positive. Okay, and the derivative of sine is a positive value, but the integral of sine is a negative value. And it is this positive or negative nature that students most often make a mistake with. So somehow or other try and get a way to remember that that works for you. But that is a most common mistake. So the other thing I want to draw your attention to is the difference between the formulae on the formula sheet, which just has sine of ax, and what's appearing in the Essentials textbook, which is ax plus b. Now the only difference is the text, that actually the Essentials textbook's got something weird here, but ax plus b works just as well. And what this does with the plus b, the only difference is in the formula, you have a plus b in the trig function as well. And it allows you to ask more difficult questions where you have to work with fractions of pi on 4 and all sorts of things. So that's one thing to watch out for. The other thing to watch out for is that pi is in fact a constant. Okay, so when you're differentiating with respect to x, your pi is a constant. So the integral of pi dx is in fact pi x plus c. So you need to remember that, and you can do on your CAS calculator, you can do a derivative with respect to theta. It's possible to do it on the CAS calculator. Theta is on the pi button, or you can just type the word theta using the alphabet keys at the bottom. But however you do it, if you do work with dx and x as your variable on your CAS calculator, make sure that you write the final answer in with the correct variable. So if the question in the exam is using theta, the answer needs to be theta equals. And also with your setting out, and you'll see this quite often in SACs and exams, is that someone will write the integral of sine of theta and then they'll just automatically put a dx here. So be really careful that whatever you're d'ing is in fact the variable that you're using in the question. So just watch out for those things. Those things are tiny little mistakes, but they lose marks in SACs and exams. So watch out for those. One of the nice things about finding the area of a circular function is that if the circular function's not translated up or down in any way, then you have symmetric areas. So here's a circular function. I don't know whether it's a section of a sine curve or a cos curve because it's kind of chopped off. But what I do know is because it's a circular function, that this section here has exactly the same area as this section here. So if I needed to find the overall area, I could work out just one section and then double my answer to get the complete area altogether. The other thing that you need to be aware of with circular functions is your transformations, because your circular functions definitely have a lot of x-intercepts. So you'll be needing to chop stuff up into sections. And so I want you to have a think about, how do you know, using your values of a and c, whether a particular function has an x-intercept or not? So if we think about it in generic terms for our function, our plus c puts our median value, so our middle value that would normally be on our x-axis, as the median value where the graph tips up and down from, and our a value as the amplitude from there up and down. So have a think about, what are the restraints around the values of a and c that you can use to tell you whether something will or won't have x-intercepts. So where I'm holding it at the minute, there's no x-intercepts. From here on, there's x-intercepts that I would need to find all the way down to here. And then I've just got one x-intercept just there. So have a think about those. Now let's have a go at some questions. So this is a classic sort of question, and because it just asks you to find the definite integral, we don't have to worry at all about positive areas and negative areas. We only need to worry about those signed areas if we're asked to find the actual area. If we're given an integral and we're asked to find the integral, then that's the integral that we find. So our first step is, of course, to find an antiderivative for this function using our pattern. And so our antiderivative, the value that comes out the front is the a value, which is the 2. And so the 2 comes out the front as negative 1 on 2, and our 2 stays in the second, in the bracket in our trig function, and our 2 terminal points go on the end, and our pi on 4 just kind of sits there. We just copy it straight down. Then we substitute our values in, so substitute in pi on 2 first, and then take away our antiderivative with 0 substituted in for theta. Now I'm going to tidy these up so that I know exactly what I'm working with. So now that I've got negative a half cos of 5 pi on 4, so I'll need to work that out in a sec, minus, and you can see I've still got my brackets around the second part, negative a half cos of pi on 4. If you wanted to change this to a plus, perfectly fine, go right ahead. I'm going to leave this bracket sitting here until the end. So cos of 5 pi on 4, so 5 pi on 4 is in the third quadrant down here, and that means it has a negative cos value, and cos of pi on 4 is 1 on root 2 or root 2 on 2, whichever way you want to write it. And cos of pi on 4, of course, is in the first quadrant, so it's going to be cos of root 2 on 2 or pi on 2, whichever way you want to do it. But there you go, there's the 2 answers there. Now what's going to need to happen is I'm going to need to do some algebra to tidy this up. So go ahead, and here's one I prepared earlier. And then finally combine the 2 together to give me root 2 on 2, if I finally get that out the way. Goodness me. There we go. Root 2 on 2. So you need to make sure that you are remembering your exact values for your trig functions and your quadrants that are positive and negative for your sine and cos values. Let's do another example. So this last example says find the exact area. So don't forget this word exact has an exact meaning and implication for us in methods. So we're going to have some kind of possibly square root number or pi in our answer, but it needs to be exact, no decimals. Find the exact area bounded by the curve y equals cos of 2x and the x-axis and the lines x equals 0 and x equals pi. Right, so the very first thing we need to do is you need to know what the graph looks like. So you can either use your CAS to sketch it, or you can sketch it using the fact that the period is going to be 2 pi on 2 because of this 2 here at the front, so 2 pi on 2. So our period is pi. It's a cos graph, so we can sketch ourselves up a very quick cos graph. It looks like that. And so the area that we're talking about is the area that is bounded by the curve, the x-axis, and 0 and pi. And so the area that we're looking for is this area. So we've got 3 areas there, and we can use our symmetry to know that halfway along here is pi on 2, and that halfway between those two becomes pi on 4, and halfway between pi on 2 and pi is 3 pi on 4. And then we can go through the process of writing our separate integrals, recognizing that for this area between pi on 4 and 3 pi on 4, that is going to be a negative value. And so we're after, the integral is going to be a negative value, and so we're after the positive version. So you can see I've got my absolute value symbols here. Now this is going to be an absolute nightmare to work out. It's going to take me forever. So surely there is something that you can do that will make it a little bit quicker. Oops, that went a little bit too far. So we can use symmetry to make it quicker. Absolutely. Can you see where it's symmetric already? So what we've got, this little section here is exactly the same as this little section here. So I can use the area from 0 to pi on 4, work it out once, it's the same as that, and then if I divide this lower section in half, I actually have exactly the same size here and here and here. So in total, I've actually got 4 of those areas, and that looks like a much easier thing to work out than this horrific thing up here. So always look for with trig functions, always look to see if there's something symmetric that you can use that will help it make it easier for you, rather than having to go through and just churn your way through this methodically. So this is thinking at a little bit of a higher level, looking for these areas that are the same. It'll save you some time, so always look for them. Unfortunately, if you start getting translations up and down, some of the areas are not so symmetric, so just watch out for that.